All right, good afternoon, everybody. We're going to be looking at lesson 1.2 today. This is on page 10 of your unit handout, and it covers limits. I know that many of you would have questions from yesterday's assignment, but you're going to have to hang on to those questions, and when we get the class started tomorrow, I'll spend some time going over any questions that you have from yesterday's work, as well as any questions that you have coming out of today's work. We're looking at doing a couple of things today. One of them is understanding the meaning of a limit, and really that's all about just making sure that you understand the notation and what a limit is telling us. And then we're going to be evaluating limits. Now, there's something called continuity, and because I'm not in class today with you, I'd rather not get into a discussion of continuity. The explanation of continuity is something that I would rather just be there with you in person, so that at each step, if you have questions about what's going on, you can ask them. Otherwise, I'm just going to be wasting my time. So we won't talk about continuity today. A little bit of background here. The limit of a function is given by the symbol L. I'm just using L as an abbreviation. So rather than saying limit, I can say L. The L is not a big deal. It's not the important part of what's going on. The actual limit notation is this, and what this expression is, that I've highlighted, is a number that f of x gets closer to as x gets closer to the value of a. So a is a particular number, and I'll give you an example dealing with specific numbers in a second. But the bottom line is, as x gets closer and closer to some number, if the function gets closer and closer to some value, then we say that that value that the function is getting closer to is equal to the limit of the function. As an illustration, I have up here that statement, and I would pronounce that statement by saying it's the limit of the function as x approaches 1 is equal to 4. There's other ways you can say it. I would prefer to say instead, it's the limit as x approaches 1 of the function, and it's equal to 4. What does this mean? Well, it's not really a difficult, complicated thing. What it means is that when the value of x that goes into the function gets closer and closer and closer to being equal to 1, but never being equal to 1, then the value of the function will get closer and closer and closer to being equal to 4, but never actually equaling 4. Remember that the function, when we talk about the phrase the function is the y coordinate. So when I plot a graph of y equals f of x, y is f of x. So the value of y is f of x. And what that means, if you look up here, is that as x approaches 1, f of x approaches 4, and that tells us that as x approaches 1, y approaches 4. That's as simple as it gets in terms of an explanation. The limit as x approaches 1 of f of x is equal to 4 means when x gets closer to 1, y gets closer to 4. And if you're like me, the first time you see this, you kind of go, what's the point of all this? The point is it's going to introduce to us a tool that can solve a lot of very, very complicated and valuable problems. So as a warm-up, consider determining the value of this. I want to just bring this down here so that we can talk about it a bit. What this is asking is, it says the limit as x approaches 3 of 2x minus 6 over x squared minus 5x plus 6. What it is saying is we have to figure out what this expression will get closer to if we start putting in values of x that get closer to 3. So as x gets closer to 3, what does this get closer to? That's what we're talking about doing here. In order to evaluate this expression, we need to investigate what happens to the function when x gets closer and closer and closer to a value of 3. Incidentally, what the function happens to be equal to when x is 3, we don't particularly care about. In fact, in this particular function, if you go to put 3 in for x, you're going to get an error because you're going to be dividing by 0. So we're not interested in at x equals 3. We're interested in close to x equals 3. So I've got some tables set up here, and the tables are in your notes and they're already completed. I want to point out to you that we have two tables. One is where x is less than 3, one is where x is greater than 3. So what we're going to be doing is putting in values of x that are getting closer to 3 from the left of 3, and we're going to be doing the same from the right of 3. So if I put 2.5 into this expression, it turns out that the expression is equal to 4. And when I put 2.75 in the expression, it turns out that the expression is equal to 2.6. So I'm going from 2.5 to 2.75 for x. The idea is I'm choosing an x value that's getting closer and closer to 3. And if I choose 2.9, which is even closer to 3, I can see what the function is equal to. 2.99 and 2.999 give me numbers that are very, very close to 2 as an output. If I go on the other side of 3 and use, say, 3.5, when x is 3.5, I get an output of 1.3. When it's 3.25, it becomes 1.6, and you've got the numbers in front of you. The bottom line is we can see that what's happening is the y-coordinate of the graph, or the value of the expression, or the value of the function, is approaching 2. It's squeezing in on 2. When you take a look at what's going on here, these numbers are progressively getting closer and closer to 2 from being greater than 2. And when you look at what's happening here, these numbers are progressively getting closer to being equal to 2 from smaller than 2. So that's why I say they're squeezing in on 2. And as a result, it appears as though the limit as x approaches 3 of this function is in fact equal to 2. And I will tell you, it is equal to 2. What we just did is not how we want to find limits, but the answer is the limit is equal to 2. All right, just a couple of notes here, and I've already alluded to this. When we're finding a limit, we're not interested in the value of the function at a certain point. We're interested in the value that the function approaches as the graph gets closer to a certain point. Sometimes the point does not even exist. And in fact, in this warm-up exercise, x equals 3 is a non-permissible value in the expression. So you could never put 3 into the expression. I do have this word at the top, necessarily, and I'm just pointing out that there will be situations where we are interested in the value of the function at a certain point. Okay? But that's not the primary concern. What we're going to do now, I need to clean a few things off of this. What we're going to do now is we're going to look at the graph of that function whose limit we were interested in. And we're going to use the graph to explain why the limit as x approached 3 of the function was equal to 2. So this is a rational function. I'm going to be using a lot of Math 30-1 information here. And because some of you have not completed Math 30-1, you're kind of out of the loop, but I wouldn't worry too much about it. Think of it this way. When we finally learn about these functions in 30-1, you will have already been introduced to them. One of the things we learn in Math 30-1 is if you want to analyze a rational function, you need to make sure that that function is factored. And in the numerator of this rational function, we can factor a 2 out and be left with x minus 3. And then in the denominator, we've got a very simple cubic, quadratic. I shouldn't say cubic. We've got a very simple quadratic polynomial expression with 3 terms, and it factors into x minus 3, x minus 2. So one of the things we note is that because of the denominators, x cannot equal 3 and x cannot equal 2. Now, how those non-permissible values reveal themselves to us depends on the other factors in the expression. If you have factors that cancel, then the non-permissible value corresponds to a hole in the function. So we're going to have a hole at 3 comma something. If the non-permissible value is the result of a factor that does not cancel, x minus 2 does not cancel, then the non-permissible value is the location of a vertical asymptote. A few other notes here. And again, you would learn about this in detail in 30-1. Since the degree in the numerator is smaller than the degree in the denominator, you're going to have a horizontal asymptote on the x-axis or at y equals 0. So I'm going to start to build this function. We're going to have an asymptote on the x-axis. We are also going to have an asymptote at x equals 2. And we have a hole where x equals 3. And in order to determine the y-coordinate of the hole, you put 3 in for x in whatever is remaining after the canceling. So the y-coordinate of the hole will be 2 divided by 3 minus 2. Well, 3 minus 2 is 1, so you get a y-coordinate of 2. And that means over here at 3 comma 2, we are going to have a hole in the graph. And I don't really want to get into the other features of the graph here. We'll just draw the picture now to save a little bit of time. The function will look like this. It will have 2 branches to it, and it will look like the following. The hole is the significant feature of this graph in terms of the limit. Remember that we want to explain why the limit of the function as x approaches 3, we want to explain why that limit is equal to 2. And here's the basic explanation. The basic explanation is that as x gets closer and closer and closer to having a value of 3, y will get closer and closer and closer to having a value of 2. So as x squeezes in on that 3, y squeezes in on that 2. And you'll notice that x never reaches 3. X can't reach 3 because there's that hole there. But the closer you get to the hole, which incidentally is infinitely small, the closer you get to that hole, the closer the y-coordinate gets to being 2. So that's the meaning of the limit graphically. All right, let's calculate some limits now. We're going to be using what we call intuitive reasoning, which means common sense. And common sense is not always the best way to go. In fact, sometimes it's absolutely a fatal move in mathematics. But I will tell you it works here. So here is my reasoning. We're asked to determine the limit as x approaches 3 of 2x minus 1. So to me, as x approaches 3, it makes sense that 2x will approach 6. Now just think about that for a second. The number that x is getting closer and closer and closer to 3. So 2 times that number that's getting closer and closer and closer to 3 should be getting closer and closer to 2 times 3. And that means, intuitively to me, the whole thing should be approaching 5. Over here, if x is approaching negative 2, to me, that makes sense that 2 divided by negative 2 would approach negative 1. 2 divided by negative 2 is negative 1. And I'm sure there are going to be some of you that are going to say, well, can't we just put in the value of x into the expression and see what we get? And the answer is, of course you can. Of course you can. But it won't always work. So if I were to just put in 5 for x, if I were to just go ahead and put 3 in for x, which is what x is approaching, then I would get 6 minus 1, which is 5. If I were to just go ahead and put negative 2 in for x, which is what x is approaching, then I get negative 1. It works. There's a catch to that we'll talk about in a few minutes. What is the limit as x approaches 8 of the number 32? The answer is 32. If 32 doesn't depend on x, then what we would say is it's always going to be 32. And I know that there might be the odd person that goes, well, come on. If the number is 32, how can we say it's approaching 32? And I understand that argument, but there's a mathematical theorem which defines the limit of a constant. And it says, as x approaches any number you want, a constant will always approach itself. And that's something we just need to remember. Over here, if we were to put 10 in, I would have 10 over 10 plus 3, which gives me 10 over 13, and that is, in fact, the limit. If I were to put 0 in here, I get 0 plus 1 over 0 squared, which gives me 1 over 0, and that's not defined. So what we would say here is the limit does not exist. But I would like you to note the nature of the output here, that we get division by 0, but the numerator is not 0. What that means, by the way, is that as x gets closer and closer to 0, this expression, x plus 1 over x squared, takes off. It doesn't get closer to a number, it just gets bigger and bigger and bigger and bigger. To me, it makes sense that if x is approaching 3, then 7x will approach 7 times 3. 7x minus 6 will approach 7 times 3 minus 6, and the square root will approach the square root. So we can figure out what this is. I believe that's 15 underneath the radical sign. 7 times 3 is 21, minus 6 is 15. All right. There's a list of properties of limits on page 13 of your textbook. Please don't look at it. At some point, we're going to be referring to that list in order to prove calculus theorems, but I think using the list right now is confusing. I mean, you can satisfy your curiosity later and look on page 13 and kind of be wowed by everything that's there, but we don't want to refer to that. So I'm going to skip past some things. If I were here, I might have a little discussion with you about those properties. Let's look at example 2. There's a graph of a function, and you're asked to determine the value of the following limits. So what is the limit of the function as x approaches 8? Well, what that means is as x gets closer and closer and closer to being 8, what does y get closer and closer to being? Well, you can see that it's approaching 2. So this is equal to 2. Let's take a look at x approaching 1. Well, as x approaches 1, which is where this asymptote is, y doesn't approach anything. In fact, y takes off to infinity and to negative infinity as you get closer and closer and closer to 1. So this is not defined. What about as x approaches 4? Well, as x approaches 4, y approaches 3. And you'll note, I hope, that there's a fundamental difference between the limit in A and the limit in C. And that's that in one of those limits, the point actually exists, and the y-coordinate of the point is equal to the limit. But in the other case, C, the point doesn't exist. There is no y-coordinate that's equal to the limit, because that point where x is approaching 4 and y is approaching 3 corresponds to a hole. As x approaches 0, you can see on the graph that y approaches -2. It might be of interest to note that as x approaches infinity or -infinity, y is approaching 1. As you move further and further to the right, that curve gets closer and closer to that horizontal asymptote of 1. So now we're going to get into the meat of the sandwich, the heart of the matter. And that's, how do you find limits algebraically? Well, it turns out, everybody, you already know how to do this. You've been doing this, but we just haven't been calling them limits. There are 3 different situations that can arise. One of them is that the limit of the function exists and happens to correspond to an actual point on the graph. And you know that's the case when you put in a value of x and it gives you a number. So if you're able to put in a number for x and get the value of the function, then that number you get is the limit. Okay? And just to go back and show something to you, this one is a case where we just went ahead and put in the value for x, and as a result, you got a number coming out, and the number coming out is the limit. That's the first case. And in fact, as I say to you in your notes here, that's your first line of attack. Your first line of attack in evaluating a limit is to do that, is to put in that number that x is approaching, and what you get is the limit. Now, I would normally have a discussion about continuity here. I want to avoid that. There's a second case where you go ahead and try to put in the number for x, and you don't get a result. In other words, you get division by 0. However, the limit might still exist. So this is a case where the limit exists, but does not correspond to a real point on the graph of the function. And you will know this is the case when you put x equals a in and you get 0 over 0. If you get 0 over 0, then the limit most likely exists, and your job is to use everything in your mathematical repertoire to eliminate the factors that are producing the zeros, and then substitute x equals that number into the remaining expression. The third case is the limit does not exist. And sometimes what you will do when you go ahead and put x equals a in, you will get division by 0. But if you get a non-zero number on the top, this is telling you the limit does not exist. 0 over 0 is telling you it probably exists. A number that's not 0 over 0 is telling you it definitely does not. And that's why I asked you to remember the case right here where we had 1 divided by 0 and we said the limit did not exist. So there are 3 situations that you can encounter. You can encounter a number over a number, in which case that's equal to the limit. You can encounter a 0 over a 0, in which case you work to remove the zeros. And whatever you're left with, when you put the value of x in, that will be the limit. So both of these, the limit exists. The third case, of course, is when you have a number that's not 0 over 0 and the limit does not exist in that case. So now we're going to work on the examples dealing with finding limits. Evaluate the following limits or state that they do not exist. So the first line of attack is to go ahead and put the value of x in and see if you get a number for this whole expression. So I do. I get 3 minus 64 over negative 6, which is negative 61 over negative 6, I believe. Just double check my math. 3 minus 64 is negative 61. 2 minus 8 is negative 6. So this limit is equal to 61 over 6. Done. The limit as x approaches 1 of that expression, well, we go ahead and we see if we can put 1 in. And of course we can. This is a polynomial function. It's defined everywhere. And we work out what this is. This is going to be 4 minus 6 plus 2 minus 10. I believe this is going to give us negative 10. So the limit is negative 10. Now, if we try to put 4 into this expression, what happens? We would have 4 plus 4 over 4 squared minus 4. We get 8 divided by, minus 16. You get 8 divided by 0. And since the top of this expression is a number that's not 0 and the bottom is 0, the limit does not exist. Incidentally, if you factored this expression, you could eliminate the x plus 4s, but you would still be left with the limit as x approaches 4 of 1 over x minus 4. And there's nothing you can do to get rid of that x minus 4. It's there to stay. And it's the x minus 4 that's resulting in the division by 0, and that's why the limit does not exist. D, if you were to put 2 in here, trust me on this, you're going to get 0 over 0. And that means what we need to do is take this expression and do everything we can to see if we can eliminate factors that produce 0. So I factor the numerator, I factor the denominator, very basic factoring. I can see that x minus 2 is on the top and the bottom and it cancels. And now what happens if I put the 2 in? Remember that x is approaching 2. So now what happens is I will get 2 on the top over 2 minus 1. I get 2 over 1. This limit is equal to 2. And by the way, in case you're wondering, yes, you need to write this each time until you put the value for x in. E, you can see quite clearly that if you put negative 4 in, you're going to get negative 64 plus 64 on the top. You're going to get negative 4 plus 4 on the bottom. You're going to get 0 over 0. So that's a dead end. We're going to work on eliminating the factors that are troublesome. The numerator is a sum of cubes, x cubed plus 4 cubed. So it factors into x plus 4, x squared minus 4x plus 4 squared. X plus 4's cancel. Now you're free to put negative 4 in. So we would have negative 4 squared minus 4 times negative 4 plus 4 squared. You're going to get 16 plus 16 plus 16. The limit is 48. So far what we're looking at doing here, everybody, is what I've been trying to teach you from the very first day of this semester. that you factor in order to simplify. Let's keep going. If we take a look at f, well, if I were to put 1 in to this expression, I would have 1 over 1 minus 1 on the top. And on the bottom, I would have 1 minus 1. That leads me to 0 over 0, which means I have to work on eliminating the x minus 1 on the bottom. I'm going to take the entire fraction and multiply the numerator and the denominator by x. And the reason I'm doing that is to eliminate this little pesky mini denominator here. Now I have the limit as x approaches 1 of x times 1 over x is 1, x times negative 1 is minus x, over x minus 1 times x. 1 minus x on the top and x minus 1 on the bottom are negatives of each other, so we can cancel them and put a negative somewhere, which means we're left with the limit as x approaches 1 of negative 1 over x. Well, I can go ahead and put what x is approaching now in for x and get a limit of negative 1 over 1 or negative 1. The limit as x approaches 4 of x minus 4 over 2 minus root x. If you put x in, you get 0 over 0. So we're going to have to work on simplifying this expression. And we're going to do a rationalization here. We're going to multiply by the conjugate of the denominator. When I multiply out the two conjugates on the bottom, I get 4 minus x. I have an x minus 4 on the top and a 2 plus root x on the top. Same thing that just happened a couple of minutes ago. X minus 4 cancels with x minus 4 to leave us a negative 1. And now you can feel free to put 4 in for x because the denominator is cleaned out. So this will be 2 plus root 4 over 1, and then we also have the negative 1. So the square root of 4 is 2, plus the 2 is 4, times negative 1 gives us a limit of negative 4. I feel as though I might be going a little fast, but I can't ask you if I'm going a little fast. So I'm just going to keep up the pace here. We've only got, I think, 2 more questions to go. This one is the limit as x approaches 0. Of the square root of x plus 1 minus 1 over x. I mean, I've already looked at this, and I've said, after looking at this and inspecting it, if I put the value that x is approaching here and here, I'm going to be left with 0 over 0. So I've already looked at doing that. Now I have to ask myself how I can get rid of the non-permissible value of x, or the non-permissible factor of x, rather, in the denominator. Well, I'm going to rationalize. Let's multiply the top and the bottom by the conjugate of the top. Which would be the square root of x plus 1 plus 1. When I FOIL out the top, I'm going to have x plus 1 minus 1. Remember that when you multiply conjugates, you square the first. When we square the square root, it goes away, and then you subtract the square of the second. The second is 1, the square of 1 is 1, and then on the bottom we have x and root, x plus 1 plus 1. This x plus 1 minus 1 is x, which means that cancels with the x on the bottom. And we're left with the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. We can go ahead and fire in that 0 now and get 1 over root 0 plus 1, which is 1 over root 1 plus 1, which is 1/2. The square root of 1 is 1, plus the other one is 2, so we get 1/2. I think this is the last example. You're going to get 0 over 0 if you try to load the value that h is approaching. All of a sudden we've switched to h. It's just a letter. We're going to see h a lot. You're going to get 0 over 0, so we have to do everything in our power to clean this up so that it will be accommodating to have h put in. In other words, we want to be able to clean it up so when we put h in, we don't get 0 over 0. I'm going to multiply the numerator and the denominator by 2 plus h because I would like to get rid of this mini denominator of 2 plus h. And I'm multiplying the top and the bottom because when I multiply the top and the bottom of an expression by the same thing, effectively I'm multiplying the whole expression by 1. When you do these problems, I've mentioned this before, you want to work downward. And yes, you need to continue writing limit as h approaches 0 until you've gotten to the point where you can sub in the number. I need to take this and multiply it by this term and multiply it by the negative 1. When I multiply the 2 plus h by the 2 over 2 plus h, the 2 plus h cancels, and then I'm left with minus 2 plus h. Of course, you don't want to write what I just wrote. That's the fatal mistake. You want to make sure that when you're subtracting, you subtract the entire binomial. And then on the bottom, we have h times 2 plus h. We don't want to multiply out that bottom because this h, right here, this h, that's the problem. You want to leave it in factored form so that you'll be able to factor it out. Now we're at the limit as h approaches 0 of, what do we get on the top? We get 2 minus 2, which is 0, and then we get negative h, and it's over h times 2 plus h. The h's cancel, and you're left with the limit as h approaches 0 of 1 over 2 plus h. And now you can certainly feel free to put in the number that h is approaching, which is 0, and we get 1/2. So the limit in this example is 1 over 2. Again, I feel as though maybe I went a little fast. That's the risk I run here of doing these videos because I don't really get any feedback from you. But the bottom line, everybody, is you have this strategy. Let me just take 1 minute to explain this strategy. When you're asked to find the limit as x approaches some number of a function, if you're asked to determine that, your first line of attack is to say, better be careful here, of a function which is f of x. Your first line of attack is to ask yourself what f of a is equal to. In other words, put in the value that x is approaching into the function. If this exists, you're done. If it exists, the value equals the limit. You're done. If this does not exist, there are two possible things that can happen. You can get a non-zero number over 0, or you can get 0 over 0. And if you get a non-zero number over 0, the limit does not exist. If you get 0 over 0, the limit likely exists. And it's this case where you have 0 over 0 that you have to do everything in your power to try to eliminate the offending factors so that you can put the value that x is approaching into the function. I don't want to spend time explaining why I've said it likely exists, but the bottom line is even though you get 0 over 0, there might be a situation where the limit still doesn't exist. And if I remember, I will show that situation to you tomorrow. Your assignment is on page 18, 1 to 6, A, C, and E for those, and then 7, 8, and 9. Do your best, help each other out, and I hope that went okay. Have a good rest of the class. I suspect that you have probably about a half hour left. Have a good rest of the class and a great night, and we will see everybody tomorrow.